The purpose of this video is to help you learn how to find the pH of a buffer after strong acid or strong base has been added to the buffer solution. Remember that a buffer solution is composed of non-negligible amounts of weak acid and weak base. When the buffer is attacked by a strong acid, well, think about it, a strong acid like HCl, acid's job is to donate H+. The acid will donate an H+ to A-, which will decrease the amount of A- and increase the amount of HA. The buffer will continue working until the amount of A- is so low that there's not really any more there for the acid to donate a proton to. Similarly, when you add a strong base, and I'll just use OH- to a buffer solution, the strong base will steal a proton from the weak acid, and that will decrease the amount of weak acid. And if you think about it, once I get rid of the H+ from a weak acid, I will convert it into the weak base, and the amount of weak base will increase. To introduce this idea, also to show you the amazing buffering capabilities of a buffer solution, I thought we'd start with a buffer problem. So a certain weak acid has Ka equal to 6.2 times 10 to the negative 7. What is the pH of a buffer of this? That's 0.75 molar A- and 0.50 molar Ha. I'll solve this like a weak acid, Ha plus H2O in equilibrium with A- plus the hydronium ion. And I'm not going to do my whole ice table, but this is 0.50. Nobody cares about the water. This is 0.75 and 0. And so you can see we'll get X times 0.75 over 0.50 is equal to Ka, which is 6.2 times 10 to the negative 7. And when I did this earlier, I found, first of all, X, which is my hydronium concentration, and I found that this has a pH of 6.38. And that number will become important after we discuss the next problem in which strong acid is added to this buffer solution. So in this problem we have the same buffer. We're going to be using 160 milliliters of this buffer, and to that we'll add 25 milliliters of 1.2 molar HCl. The first thing I'm going to do is use dimensional analysis. I want to know 160 milliliters of my buffer, what does that include? Well, that will be 120 millimoles of A-, and I determined that by saying 160 milliliters of the buffer times 0.75 moles per liter. And again, remember, I like to work in millimoles. In addition, in this buffer, in 160 milliliters of this buffer, there will be 80 millimoles of HA. Now to this buffer, I'm going to add 25 milliliters of strong acid, and it's 1.2 molar HCl, and that represents 30 millimoles of HCl. Now we know that HCl is a strong acid, which means it's going to do its job, and its job is to donate an H+ to the best base available. The best base in this scenario, yes, there's water around, but A- is going to accept an H+ from HCl. And when A- accepts an H+, it will become HA. So really, this problem is all about decreasing the amount of A- in the buffer and increasing the amount of HA in the buffer, and then finding the pH. I like to do this in my I row, as you'll see below. Alright, so let's get this set up to handle a buffer problem. And I have HA plus H2O in equilibrium with A- plus the hydronium ion. And I'm going to mess around with my I row here. First of all, I'll recall that I initially had 80 millimoles of HA, and we're going to be in some total volume here. I'm kind of forgetting right now. I didn't write it down. It ends up not being important to the calculation. And I also started with 120 millimoles of A-, and that's in the same total volume, and no hydronium ion. When I add the 30 millimoles of HCl, remember, that is going to react with and consume 30 millimoles of A minus. And when HCl gives a proton to A minus becomes additional HA. I'm once again going to take a bit of a shortcut with my ice table, and I'll simplify this ice table to X times 90 over, there's the total volume, 185. That was 160 milliliters plus 25 milliliters. And again, I'm working in millimoles and milliliters, and this 90 comes from 120 minus 30. My concentration of HA has also been impacted. I now have 110 millimoles of HA, and that's in that same 185 milliliter volume. And this equals my Ka, which is 6.2 times 10 to the negative 7. When I solve for X here, because I've solved this as a weak acid problem, X is equal to the hydronium content, hydronium ion concentration, which is equal to 7.6 times 10 to the negative 7, if I've done everything correctly. And that means that I have an ultimate pH of 6.12. By way of comparison, the pH of this buffer before the addition of the acid is 6.38, and if you see, adding acid makes the pH go down, which makes sense, but adding acid doesn't make the pH go down very much. That's because this is a buffer, and buffers protect against pH change.